Lorenzo Casini from University of Bologna. The topic is high-level causation and causal inference.
So first of all, I'd like to thank the organizers for putting together such a nice event and for inviting me to present my research. So I'm going to talk about, I presented this stuff already and I've never pitched it this way, but say this time I'm going to say that I'm going to talk about a history of interaction between philosophy and science, where initially philosophy draws from a scientific method to clarify a problem of definition of a concept of interest to philosophers, namely causality, and then tweaks these definition in such a way that these definition can be used or should be used to solve another problem of traditional interest to philosophers, namely the existence of mental causation. And then I want to show how these tweak can fire back in the sense that the new theory you developed to justify this controversial theory of mental causation doesn't align well with the scientific method and scientific practice you started off with to solve the first problem of definition of causality. Okay, so it will become clear as I go along. Okay, so as you know, the classical problem of causation is that correlation is not causation. So we may observe that two variables are correlated, and we may ask, does one cause the other? So does X cause Y? Well, the answer is not trivial because there are several possible explanations besides causation from X to Y for why we observe this correlation. There's clearly the possibility that X is indeed a cause of Y, but there is also the possibility of reverse causation. It could be Y that is a cause of X, or it could be simply that X and Y are coincidentally correlated due to the existence of a common cause that induces a dependence between them. So you are in a situation where you don't know which one of these models is true, so you don't know whether X causes Y. Now, there's been an attempt to define causality in a way that at the same time reconstruct ideally the reasoning of scientists who in their everyday practice experimentally try to solve this problem of identification of causal relations, namely Woodward's theory of causality. So it's called interventionism because it's based on the key notion of an ideal intervention, yet in a nutshell, the theory says that X causes Y if and only if there exists an ideal intervention I on X with respect to Y, such that one may use I to change X, that would be the putative cause, in such a way that Y, that is the putative effect, changes too. And in that case, you're entitled to say, to conclude that X indeed causes Y. And if X causes Y, it will also be true the reverse. So there will exist an intervention that does such and such. Okay, so crucially, the account depends on the notion of an ideal intervention. The definition is presented in Woodward's book is long. I'm not going through it by reading it. I'm just going to very quickly illustrate the gist of it. When does something count as an ideal intervention? First of all, the ideal intervention has to be a cause of X. That already tells you that what Woodward is doing is to explicate the notion of causation with the appeal or to other notions. He finds it unproblematic as long as this appeal doesn't refer to the particular notion of causation between X and Y that he's trying to explicate. So he's using the causation between I and X, for example, to explicate the notion of causation between X and Y. Okay? So I has to be a cause of X. Not only I has to act as a switch for the other variables that cause X. What does that mean? Basically, I has to fix X in such a way that it makes X independent of its other causes, whether they are known or not. That's the idea. Because in an experimental context, the experimenter may not even know what these causes are, but as a result of fixing X, you're making X independent of its existing previous causes, okay? So imagine you're testing a new drug by assigning the drug to the treatment and the control group, you're fixing the dosage of the drug in the bloodstream. That dosage is going to be a value of the variable x, which is going to be independent of other possible causes of that variable. That could be the presence of the drug on the black market, for example. If the experiment is controlled, people aren't allowed or shouldn't be allowed to get out and get the drug on the black market, or if they feel they belong to the control group, they shouldn't be allowed to do that, because that would basically prevent the experiment from telling us anything in a conclusive way. Another condition is that any directed path from the intervention to the putative effect has to go through X. What does that mean? But basically, it means that the intervention doesn't have to directly or indirectly via other variables affect the putative effect that would basically undermine the credibility of the experimental result. Imagine you're trying to test whether aspirin is effective in relieving headache. It would be a very bad experimental design, one where you at the same time give the tablet and hammer the patient on the head. So that would be basically useless to learn whether or not aspirin relieves headache. So that's not allowed. Also, the intervention has to be statistically independent of any variable Z in the background that may happen to cause Y, and that is on a directed path that doesn't go through X. Okay, so it shouldn't happen that I just so happen to be statistically correlated with a common cause of X and Y. That would also be something that introduces confounding in your experimental scenario. So the latter two conditions together guarantee what is called no confounding, whether this is direct or via off-path factors such as Z, in such a way that given an intervention I, which is used to change X, any dependence you observe between X and Y post-intervention can only be imputed to X causing Y. So the observation allows for just one interpretation in ideal scenarios, when that intervention exists and is correctly implemented. Okay, so let me come to the topic of the problem of I wanted to address in the talk, namely how should causal inference proceed in the context where you not only have like variables that have, say, reductive supervenience basis, but there are also no reductive supervenience basis involved. So many variables in the special sciences stand in non-causal relations to more fundamental variables. Here are a few examples. So COVID-19 stands in a say, supervenience relations with the variants of COVID-19. There are many ways in which COVID-19 can be manifested or instantiated. It can be variant alpha, beta, gamma, delta, and so on and so forth. Total sales in macroeconomics, they can be uncoupled as domestic and foreign sales. Or to make a more trivial everyday, but also toy example used in philosophy, total cholesterol is made of good and bad cholesterol. Now, depending on the people you talk to, they will have an intuition about the existence and labeling of these non-causal relations, even though the labels they will be will depend on the discipline they work on. So philosophers may talk about supervenience, so one variable being necessarily dependent on the variation of the supervenience base X. There's no change in X without any corresponding change in the supervenience base, but not the other way around if the supervenience is no reductive, okay? Or they may call it constitutionally, for example, they are working in the field of mechanistic explanation and think that the interlevel relation between a phenomenon and the components has to do with constitution. But if you talk to scientists, they typically will talk about aggregation. So total sales are an aggregate of domestic and foreign sales or composition. Okay, besides terminological problems, what is important here is that the presence of these sort of variables in a variable set, when you investigate causal relations, can create problems for causal inference. This was originally observed by Spiritis and Shines in 2004. They say that if the constituents of X, which is your putative cause, are unobserved, and they have heterogeneous roles with respect to effects of interest. So in this case, the supervenience space of X contains variables that have heterogeneous roles with respect to Y, then one faces the risk of ambiguous manipulations. What is going to be the effect of changing X with respect to Y if I don't know what effect it has on the supervenience base of Y, knowing that this supervenience base is heterogeneous? For example, what is the effect of manipulation on total cholesterol with respect to heart disease? Knowing that total cholesterol alone doesn't tell me much. What is important is the ratio between good and bad cholesterol. In a more recent paper, together with co-authors, I presented a framework where these two kinds of relations appear together, and there we say that the aggregates that are made of heterogeneous constituents with respect to the effects of the supervenient bases are called ill-defined. And in that context, we also give a partial solution of the identification of ill-defined causal relations, we call them in that context. But we don't need to bother with the result obtained in that paper. So basically what is important here is that X would be called ill-defined because it's composed of variables that have heterogeneous causal roles with respect to other variables, okay? And then one can ask the question, does total cholesterol cause heart disease at all, okay? So it's not really whether or not good and bad cholesterol cause heart disease, but you can ask the question, does it cause it as a whole or not, okay? Independently of how predictive it is, okay? That seems a legitimate question to ask. Okay, so let X be ill-defined to whatever degree, namely to whatever degree of heterogeneity between the constituents of X with respect to the putative effect of interest. Let's grant that causation between X and Y is possible. So let's grant that something like the mental causation problem has already been solved. That's not going to be the topic of my talk today. Let's also grant that scientists that infer to the existence of this relation between X and Y can be justified. So they work in special sciences, they observe these aggregate variables, they try to infer causal relationships between these aggregate variables, and they tend to conclude sometimes that they have good evidence that they found some, okay? So let's take science at face value and try to understand what rationale there could be behind these statements, okay? What could possibly justify their method? Even if, as it happens, this is crucial, they do not observe or even know what these supervenient bases are. And notice the strict parallel between the previous scenario I presented, where I said in a randomized trial, you want to know what X causes Y, even if you don't know what these background factors could be that could mislead you to believe that there is a causal relation between X and Y if you don't perform the experiment properly. You know that if the design is correct, it doesn't matter what background factors there are in the background, okay? The result has an unambiguous interpretation. Now, translate this in this new context where it should also hold that supervenient spaces are unobserved, because scientists do not observe, don't even know what they are, these supervenient spaces. Often, we talk ex post about aggregate variables of known components, but because we do know what the components are. But scientists typically have no idea of what the relevant components are. They just know that this is what they observe. They have no idea of what composes them, okay? So the question is, may interventionism or a revised form of interventionism rationalize the inference in scientific practice to a conclusion of the form X causes Y, when X may be a variable that non-reductively supervenes on heterogeneous components? Or, in case the reply to the first question is negative, does one need an alternative reconstruction of this scientific practice, okay? So please let me know how I'm doing with time. Okay, I should have still 20 minutes before discussion, okay? I'd be happy to discuss 5 to 10 minutes. Yeah, okay. Okay, so I'll briefly walk you through the modified theory that is supposed to solve the meta-causation problem, and I will take for granted that it does, okay? I won't contest that result. And then I'll see how this theory fares with respect to the problem of applying it back to scientific practice, okay? So, the original problem of meta-causation is Kim's causal exclusion argument that questions the compatibility between the existence of mental causation and non-reductive physicalism. Okay, I won't walk you through the whole problem and the way in which this contradiction arises between premises that all parties seem to assume. But basically, the question here is that some interventionists have asked is, can I use interventionism to solve the problem of mental causation? So can I prove that mental causation exists by using an intervention on a variable that non-reductively supervenes on a physical substrate, for example, a mental variable, to establish that that variable causes something else? Because if I could, well, that would be very good news and surprising news, because I could use empirical methods to solve a metaphysical question, okay? So something that is believed to be beyond observation or testability would be solved by empirical methods. So the first hunch is, yes, if I intervene on X, I observe a change in Y. I can conclude that X causes Y, not in the sense that X is sufficient for Y, but in the sense that X is relevant for Y. So there's no denial that the supervenience base is causally sufficient to the supervenience base of the effect, but at the same time, there is a claim that there is no incompatibility with the claim that X is also causally relevant to Y. So in this sense, there's no competition, and I can claim that X causes Y, okay? Now, the immediate reply is, well, I can't, because if I use the notion of idea intervention as defined in the theory, I would need to ensure that all of path variables are kept fixed. For example, the supervenient base of X would be alone enough to induce a change in Y that could equally well explain why Y changes. Now I have to hold it fixed, but if I do that, then I prevent X from changes, because X changes only if the supervenience base changes. So that is an off-route path that if I hold fixed, I don't get any evidence that could possibly verify the claim that X causes Y. Now, Woodward's reply is no. I mean, yes, I can establish causation as long as the relevant notion is amended. So I'm happy to go a few minutes over time if it's allowed, even that I start a bit late, and also because the talk is a bit longer than I expected. I have to add exemption clauses to this non-confounding condition. So I just have to allow the supervenience bases need not be kept fixed. I have to revise the definition of an ideal intervention. Now, here the problem arises that if I do that, then there will be two observationally equivalent models that are equally capable of explaining what I'm observing. The model where I do allow for mental causation, and the epiphenomenalist model where I don't. Interventions so construed in this relaxed way would be insufficient to decide between which one of these two models is the true one, given the observations that I receive. I mean, there's nothing in the observations that speaks in favor, definitely conclusively in favor of one model rather than the other. Okay, Woodward has recently replied to this objection of underdetermination, saying that, well, we have to tweak a little bit the notion of causation. Okay, X causes Y if there is an intervention on X that changes Y, but an additional condition is that this change has to be non-ambiguous, okay? So it has to be a change that allows us to non-ambiguously predict the value of Y. Now, if there is a causal heterogeneity in the supervenience base of X, this is going to undermine our ability to predict non-ambiguously the effect on Y. Think about the total cholesterol case, okay? In that case, he would like to conclude that since total cholesterol is a variable made of two heterogeneous variables. I have no way to change total cholesterol in a way that allows me to predict non-ambiguously what is going to happen to heart disease, because I don't know what is going on with good and bad cholesterol. Okay, so the relationship between these two variables may lead to a change in Y, but this change is not unambiguous. It doesn't allow me to predict. Okay. So he adds a realization independence condition that says that the effect has to be conditionally independent of any other intervention that changes the supervenience base consistently with the value that X has been set to by the first intervention. So you fix total cholesterol to 100, and then you intervene on the supervenience base in a way that is consistent with that value. So say you change the ratio between good and bad cholesterol from 60 to 40, to 40 to 60, to 50 to 50, or whatever ratio you like, as long as it is compatible with the value of total cholesterol, and that should not make a difference to say the prediction of heart disease rate or probability. Okay, and clearly it does, because depending on these fine-grained changes, there's going to be a difference. So he will say that given a revised version of the theory of interventionism that includes this clause, you're able to disentangle between the two models. There will be cases where the putative cause is insensitive to these changes in the supervenience base in such a way that the effect is always going to stay the same for certain values of the cause. And there will be cases where there is no value of the cause that is so insensitive, okay? Like, for example, the case of total cholesterol. In that case, it would say that the Shrow model is the one without higher level causation, and the other model that postulates it is incorrect. Okay, so now comes the practice part, okay? This problem, let's assume that he managed to solve the mental causation, this theory, the mental causation problem. He adds, a number of readers of this article were sympathetic to the exclusion argument and responded to my discussion by drawing a sharp distinction between the argument as methodological proposal and the argument as metaphysical proposal, okay? And he believes that it should still be of interest to philosophers of science and methodologists with practical interest to understand how we should think about interventions and their use in causal reasoning when supervenience relations are present. So he believes that what he has given is a theory that has applications in line with scientific practice, okay? So the question is, can interventionism, this new version of interventionism, rationalize the inference to X causes Y, given that in practice the supervenience based is typically unknown or unobserved, okay? So we are going to conclude that this is not the case. There are two possible interpretations that we can give to the new theory, depending on what Woodward himself says. There's a strict interpretation that depends on the strict interpretation of the realization independence condition that says that that leads to the conclusion that causal inference is generally unwarranted by the modified theory. And there is a relaxed interpretation of that condition, under which the new theory is too weak to allow us to distinguish between observationally equivalent models. So this is going to be our negative conclusion. Then we have a positive proposal that I hope I'll be able to sketch. Okay, so can scientists reliably use the new notion of intervention in the same way they could use the old one? As I said, you don't need to know all the causal context. You can use interventions by designing good experiments like randomized control trials, and the correct design should grant the conclusion of the study, even if some confounders are unknown. This is not so for the new theory interventionism. The design grants the conclusion only if realization independence holds, but that means that basically you have to know what the constituents are. So you would need to know whether tweaking the constituents does make a difference to the putative effect or not relative to the fixed value of X. Otherwise, you can't satisfy the conditions of the new theory, okay? So the question is if the constituents are unknown, is realization independent perhaps warranted nonetheless? Because if that is the case, I mean, the proposal would work in practice. If it happens to be warranted, typically, then it's all fine. Okay, so imagine we are in this situation where X could be, say, total cholesterol, and U1 and U2 are the constituents of total cholesterol. The double arrows indicate non-causal relations, okay? And I is the intervention. Now, clearly, an intervention that changes X only does that through changing the supervenous base of X, okay? There's no other way in which X should change other than by changing the supervenous base of X. And clearly, depending on the way you tweak the supervenous base of X, you're going to have different effects on Y, okay? So we can say that conditional independence, realization independence, that's another name for the condition. Conditional independence between Y and U1 and U2 given X, so basically the irrelevance of U1 and U2 for the ambiguity of the relation between X and Y only obtains for special configurations of parameters. So you have to tweak U1 and U2 in particular ways for there to be no observed difference in the putative effect Y. From which it follows that in generic cases, without this special tweaking, realization independence will be violated. Okay? So this simple linear model I presented, there's no reason to assume why it should be inexistent in scientific practice, since there is no reason to assume that it's rare. Then a scientist that doesn't know that this is the case, the relationship between the variable and its supervenous base can't exclude that the relationship is spurious because realization independence is violated, okay? Okay, what is the fix? Well, Woodward suggests that perhaps the condition could be relaxed. The problem with this suggestion is that without observing the supervenous base, we cannot tell when realization independence holds even approximately, no matter how exactly the concept of a relaxed realization independence condition is operationalized. Okay? We wouldn't be able to tell how closely realized it is satisfied. But in any case, let's grant the realization independence is relaxed. Now, can NIV star intervention establish causation is if the constituents are not observed? Here we have to note there is a stark distinction between traditional experimental context and these new contexts that I'm discussing now. So typically, experimental designs are not flawless, okay? We do our best to have a controlled experiment, but there could be biasing factors, okay? But luckily, the Gould theory had implications that indicate that certain evidence or observation count as indication of the experiment being flawed, okay? So, for example, if everything goes well, there shouldn't be any confounding, okay? Variables in the background should not influence the conclusion. However, what scientists typically do ex post is to check whether the intervention was in fact well conducted. I mean, they don't stop believing that the design is perfect. They do these checks. So they test for certain covariates to see whether or not the relation between the putative cause and the effect is stable. Okay, if it is not, then there is the possibility of uncontrolled variables in the background. Another way in which they proceed is to check whether there is an asymptotic convergence of the estimating. That again indicates if there is no asymptotic convergence, it indicates the presence of unknown or uncontrolled confounders. So basically, if there's no way that the estimate converges to a precise point estimate, it could be that there are confounders varying in the background that prevent this convergence. Okay, so that means that again, the experiment is invalid. It's an indication that it is invalid. Now, can I use the same kind of implications to conclude that my experiment is valid when I don't observe these indicators of invalidity in the new context? Now, there are two cases. The experiment may be invalid if there is one covariate that strongly affects the estimate. That would be G, okay? That would be the traditional case of confounding, where I'm hammering the patients in the head, okay? That would be the traditional case where G is different from 0. There is the traditional case of confounding. But it could also be the case that the experiment is valid because there is no such confounding going on, that coefficient is 0, even if, note, the intervention violates strict realization independence, since strict realization independence is no more assumed, okay? So there are two scenarios. How could one find out which one of the two is the case? Because one is a bad scenario, okay? The one where I'm introducing confounding. That's bad. So the conclusion should not be accepted. The other one is innocuous if realization independence is relaxed. So I should accept the conclusion in that case. And now, controlling for all possible covariates is simply impossible, okay? So that's not a viable strategy. You can't rule out the presence of all possible confounders. Could one rely on non-convergence? That was the other indicator of a good experiment in the traditional case. It turns out that you can't, because basically the convergence depends crucially on two conditions: on the homogeneity of the components in the realization base, and the constancy of the confounding factor. So 0 is a particular case of constancy, okay? But it could be also a different context, constant. In that case, you would have a biased estimator, but still you would observe convergence. So there are these two conditions on which convergence depends. They are necessary for convergence. Now, the lack of convergence means that one or the other is not the case. Which one of the two is not the case? We can't tell. So the non-convergence cannot invalidate the experiment because it's now compatible with two different but observationally equivalent scenarios. And this is very basically what illustrates the situation. This is a case of first, it's a case where we want to say that there is causation, even though there is no perfect realization independence. The second case is one that is different. So you see, there are only simple edges. There are no non-causal edges. All edges are simple. That means that U1 and U2 are just traditional causes of X. They are not constituents of X, which means that X can change not just as a reflection of a change in the supervenience space, it can also change independently. It's just contingent that it changes depending on changes in the causes. You could also affect X independently, or change it independently. And ideally, this is what an ideal experiment should do, right? You should fix X in a way that makes it independent of its previous causes, say availability of aspirin on the black market, and as a way to test whether X is a cause of Y. Now, let's assume that in this particular model, X is not a case of Y. Such experiment would probably find no correlation between X and Y if it is well performed. Okay, basically it turns out that given these two models, for any parameterization in 1, there's another parameterization in 2, such that the coefficients beta of the regression of y on x are the same. So basically, the bottom line is the following. If you do observe x and y, but you do not observe U1 and U2, you won't be able to tell which one of the two models is correct, because whatever you find could as well have been produced by another structure which is incompatible with that structure. So whether it is partly ambiguous causation or whether it is spurious correlation, you can't tell, okay? So the convergent properties cannot distinguish. This is an illustration. So to recap, let's assume that high-level causation exists. How long have I got?
There's now 6 minutes left for discussion.
Thanks for discussion. Okay, I'll hope to wrap up in 2. So assume that high-level causation exists, and we've demonstrated up to now that the inference to high-level causation in interventionism is problematic because apparently the account doesn't explain how you can become justified that there is a relation of causation between two variables if the supervenience bases are unobserved. Okay. Now, if scientists are not systematically misguided in their practice, they cannot follow this normative criterion in their practice, not even implicitly, because that would lead to wrong conclusions. So we need an alternative rational reconstruction of what they are doing if we want to understand how they become justified in making these inferences. Okay, so here comes a brief look at our proposal. So the situation is the same. We have an observational equivalence between these two models. Yes, they are observational equivalent, but they have different implications. In what sense? Well, if the second model is true, as I said, there exists some intervention on X that screens off X and Y. What does that mean? If there is no real causal relation between X and Y, and the correlation is just induced by the common causes, if I fix X by rendering X independent of the common causes, I will make the putative cause independent of the putative effect. Okay? So by doing that, I will be able to falsify that. Okay? If one is true, by contrast, there will exist no intervention that does that. Okay? There will persist a dependence between these variables. So the gist of the argument here is that the first model is falsifiable, because if I find no dependence, I can tell that I'm in the second case, but it's not verifiable. I can't conclusively conclude that the first model is correct. It is at most corroborated. Okay? So there is this asymmetry, inferential asymmetry between these two models, which means that the proposal is abductive. So what I do observe is a repeated failure at making X and Y independent, okay, in my practice, if model 1 is the correct one. Now, this failure at making it independent has two possible explanations. Always, I could always be intervening incorrectly in the second model, and the second model is true, and I still observe a dependence. So my intervention may not be ideal. If it is ideal, however, what I can conclude is that I've been able to justify the inference to one model in an abductive way. So the inference to the first model is not justified by ideal evidence. I can't gather ideal evidence that allows me to conclude that X causes Y, but it is justified by the fact that the first model explains better the evidence I have, namely the impossibility to break this dependence, than the other model. And this is the reason why I infer to that model. Okay, I won't wrap up. If you have questions, you can ask me in the Q&A. Stop here.
Perhaps time for one quick question, but after that note, we'll take another conference photo, so don't leave. Are there any questions? Okay, our special commentator, Helen B.B.
Oh, microphone. Yeah, sorry. I think this might just be a request for clarification. I guess I'm kind of not quite feeling the force of the problem. So, okay, I get that there's a sort of skeptical worry that lots of cases might turn out to be like the good bad cholesterol case. That would be very bad. Mm-hmm. But lots of cases, it seems like we've got no reason to think that it is like that. So, drug trial, right? All the drugs have been manufactured in the same place in exactly the same way. No chance that's going to be like the good bad cholesterol case. Mental causation, we might have lots of other complicated reasons for thinking that what goes on at the level of the supervenience base isn't going to be at all like the good bad cholesterol case. So I think I might be missing something, because I'm kind of like, it feels like there's lots of extraneous evidence, in many cases anyway, that will give us good reason to be confident this is not like a good bad cholesterol case.
Yeah, I have contrary intuitions. We have no good reasons to feel safe. I mean, the drug has been produced by the same factory. Yes, but the thing is that we do know how the drug has been produced, what the active principles are, what percentage is in there. But I mean, we are considering cases where we do know what the constituents are, what the supervenience base is. What I'm considering are cases where we don't. So we are manipulating variables where we don't know what the supervenience base is. So if I'm manipulating an economic variable and I have no individual data, I mean, I lack the information that you really are assuming. Like, you need to pretend to be in the situation where you don't know, basically. So you're the guy in the factory that is inspecting how the process is going on, but he doesn't know anything about chemistry, okay? So then he takes all this bunch of pills, he takes them to a controlled environment and wants to test. Now, who can convince this guy that there wasn't an evil chemist in the factory that was messing up with the ingredients? Like, for all he knows, these may not be equally distributed, right, in the pills. So this is the situation the point I'm coming from.